basically it said that to find the area underneath the curve between A and B, all you have to do is take the antiderivative and evaluate the antiderivative at the upper limit minus the antiderivative at the lower limit.
Wait, did someone teach pre-calculus before Mr. Pell? Or has he always?
Yeah, well, the way when Sue was the director, it was Mr. Pell taught it sometimes. I don't remember exactly who taught it, but it was somebody else.
Because both of Kathy Wilson's children didn't have it.
Yeah, no, they. Yeah, I forgot who actually did pre-calculus. Julie. Okay. So let's see. I'm trying to remember what we were doing. Okay, yeah. So we were talking about definite integrals, and there was this. This is the example we're going to work through. So it's just a polynomial, and it says evaluate the definite integral. The definite integral. Remember, the definite integral looks like this. It has the integral sign. It has the lower limit and the upper limit here, and we put the function inside the integral sign. We put a dx. So it doesn't say you find the area underneath the curve, but Section 4 basically tells us that. It's telling us that the definite integral of the function is the area underneath the curve. In Section 3, we said the definite integral was defined as such, and it was for finding the area underneath the curve, but it wasn't. We didn't know the fundamental theorem of calculus, so in Section 3, we would have had to use the limit definition to evaluate this. In Section 3, we would have said, oh, that's the same as the limit as delta x, or actually as n goes to infinity, of the summation from I equals 1 to n of f of x sub I delta x. So that was Section 3. That was the definition of what the definite integral was. So Section 3 was basically saying the definite integral gives us the area using the limit definition. And what Section 4 said was that the definite integral, instead of using the limit definition to find the area, you can take the antiderivative of the function and evaluate it b minus the antiderivative of a. So it's still the area. So when they're asking for the definite integral here, they're basically saying use the fundamental theorem of calculus, because we're in Section 4 now. So anyway, that's just a little subtle thing. So let me write this back again. And another little subtle thing is that, in Section 1 we said we use this symbol to represent the antiderivative without the limits. We call that the indefinite integral, and we said the dx was to tell us what variable we were integrating with respect to. So because there's a dx in there, that means we're integrating with respect to x. Now, if we talk about the definite integral, the dx really kind of says, oh, that's like the width of a rectangle with a really small width, dx. So I said when we talked about that in Section 1, it would make more sense why. Because to have both the definite and indefinite integrals have similar forms, you've got to use the dx for slightly different reasons, but it looks the same. So again, in the indefinite integral, the dx is to represent, that's what I'm integrating with respect to, whereas in the definite integral, you can think of the dx as being the width of the rectangle, and the function, the height of the rectangle. And all we're doing is we're adding up all those areas of rectangles to get the total area. Okay. So the dx is important. Don't leave that off. It's telling us something. Okay, so what we do, we take the antiderivative of what's the function. So we'll get 3 times x cubed over 3 plus 5 times x squared over 2 plus 4x. And we don't put an arbitrary constant c, we put a vertical line with the lower limit here and the upper limit there. We can simplify it a little bit before we plug it in. So first, let me just move this down a little bit. So basically what we're doing here is take the antiderivative of the function. And then the second step, of course, is to evaluate the antiderivative at x equals 3 and subtract antiderivative at x equals 1. Okay, so for x we substitute in 3, so we get 3 cubed plus 5 times 3 squared over 2 plus 4 times 3. So that's the antiderivative evaluated at 3. And then we subtract. And I'm going to go ahead and put these big brackets here just to kind of separate things. It's better to have more brackets than not enough brackets. So then we take 1 cubed plus 5 times 1 squared divided by 2 plus 4 times 1. And the rest of it's just doing fractions, stuff like that, possibly. So we'll get 27 plus 45 over 2. 3 squared is 9, times 5 is 45, plus 12. And then we subtract 1 plus 5 halves plus 4. So we get 39 plus 45 halves minus, here we'll get 5 halves plus 2 halves, 7 halves, 7 halves plus 8 halves, 15 halves. So just put it into halves, and then if we subtract 15 halves from 2 halves, we'll get 30 halves, which is going to be 39 plus 15, which is 54. So that's the answer, and that is the area underneath the curve. And we're just going to see if we can kind of convince ourselves that that's a reasonable answer. So we're going to look at the function, and let me delete that for a second. Okay, so here's the function. It's the red curve, this one right here. And we're integrating from 1 to 3. So the area that I've shown with the black, this area here, between the function and the x-axis and the 2 vertical lines, that's the area I'm talking about. So one way to do that would be to count rectangles or something like that. But there's another way of kind of approximating stuff. You could think about what if I let the function equal the value at the end of the interval. Obviously, the area under that rectangle is greater than the area underneath the curve. And if I went to the beginning of the interval, the area under this rectangle here would be less. So there's somewhere in between. And the way you do it, the way I do it, is you think about this area, which is between this blue line and the red curve, and you just try to in your head think about where would I place that blue line so that this area here is equal to that area, because this area I'm overcounting it here. I'm overestimating it, but here I'm underestimating it. And so if I pick some value that gives me the same area, and I'll just mark, I'll shade it in just in case anybody's having difficulty here. So you're going to have this area and this area. If you can do it where they're approximately equal, then that's probably the actual area underneath the red curve is the same as the area in this rectangle. So that's my guess where I would put that, because this area looks about the same as that, just ballpark. And if I go over here, I'll see the answer is 20. Here's 20, and we've got increments of 1, 2, 3, 4. So 2.5. So that would be 27.5. So the height of that rectangle is 27.5, and the width of the rectangle is 2. And I multiply those together, and I'll get 55. That's the area I'm approximating that's under the red curve by doing this trick that I do. And if we go back and compare it, that matches up pretty close to with what the exact area is. So if I had moved it down to 27 instead of 27.5, I would have been exactly right. So this area is probably a little bit larger than that area. Anyway, hopefully you believe me that that's the right answer. So what have we learned up to this point? So let's kind of review. We've learned that we have this new operation called the antiderivative. And the antiderivative is just the opposite of the derivative. It's what function, how do I say it? If you have a function, what function's derivative is equal to the original function. And we found out that you can use the processes of antiderivatives to solve differential equations. If you know y prime, you can figure out what y is. The next thing we did was we came up with a way of taking rectangles and approximating the area underneath the curve, but when we took the number of rectangles to infinity and the width to 0, we actually got the exact area underneath the curve. And we saw that was a lot of work, so we said there's got to be a better way. So we said, hey, Newton, what's going on here? And he said, hey, all you have to do instead of doing all that long stuff is to take the antiderivative of the function you're looking to find the area under and just evaluate the antiderivative at the upper limit and subtract the antiderivative at the lower limit. Now, which functions can we integrate at this point? We can integrate the functions that we know how to take the derivatives of. So, I handed out that thing the other day, this sheet, and it has basic integration formulas, and you can see a lot of them are just the opposite of what the derivative formulas that we've already learned. So on Friday we recognized, at least I did, that the integral of secant squared was equal to the tangent because I knew the derivative of the tangent was the secant squared. So there are certain functions we can integrate, but they're ones that we obviously cannot integrate at this point, which is what we're going to learn in section 5. So we're kind of limited, and that's basically 75% of the rest of the class, is to try to figure out how do you integrate functions that are not simply in this list, but how do we manipulate the functions so that they do appear in this list. If they don't appear in this list, we don't know what to do. We could make the list bigger, and I'll show you where you can get. There are, back in the old days, used to have tables. They were about this big, and they had logarithms, and they had probably 50 pages of integrals like this that they've already done for you. You didn't actually have to do them. They're called integral tables. Nowadays, we don't have to worry about that because we have nice software that does a lot of that stuff for us. But even so, we're still going to learn how to use the techniques. Okay. So before we finish this section, we've got two things to talk about. There's what's called the mean value theorem for integrals. So I'll read it and then we'll discuss it. So the mean value theorem for integrals says if f is a continuous function on a closed interval from a to b, then there exists a number c in the closed interval a to b such that the integral from a to b of f of x dx equals f of c times b minus a. We actually just did that. What I did was I guessed what f of c was, the height of that little blue line, such that when I took the height of that blue line and I multiplied by the difference in the limits, I got the same as the area underneath the curve. So I guessed it to be 27 and a half, or I estimated the area to would have been 55 instead of 54. So it says we can do that for any function, and that the value of the function, there is some f of c, and c is between a and b. So there's always some value of x where you can evaluate the function at x between a and b such that basically the height of the rectangle is equal to times the width of the rectangle equals the exact area underneath the curve. So this is a rectangle. This is not a rectangle. So let me just demonstrate it here. So we have another curve. So we're looking for the area between x equals a and x equals b for the red curve, which is above the x-axis. And we want to know what is the value of x such that the function evaluated at x would give me, multiplied by the difference in the limits, the value of the function times difference in the limits, would give me the same value as the area underneath the curve. So again, what I'm going to do here is I'm going to if I go this way, I'm obviously overestimating the area underneath the curve. And if I go down to here, I'm definitely underestimating the area of the curve. So it's somewhere between those two. And so what I'm looking for is I'm trying to see this area here, which is above the red curve, above the horizontal line, but below the red curve. I'm trying to set that equal to the area that would be in this little bit and the area in that little bit. So it's probably, I'm going to guess it's probably somewhere around here. It's going to be between those two. So what is C that makes that happen? Well, C would be the x value that results in, it's really the intersection of this line with this curve. So x equals C, there's actually two values of x, because x equals this value would give me this y value, which this y value multiplied by the delta x, or the difference in the limits or the interval, give me the same area. The area into this rectangle equals the area into this curve. But also there's a second value of x, that would be that point. So C would be the x value, f of C would be the y value, and that y value is going to, that y value here multiplied by the y value here multiplied by the difference here would give you the same area as the area underneath the curvy part. So you can show that it's true for any integral, because some parts are going to be higher than this number, and this number, let's just, what is that number called? It's called the average. Okay, so here's, if you take the intermediate you take the mean value theorem and you solve for what is the value of the function where it times the difference between a and b equals the area. If you solve for that function, it's going to be the integral, the actual area underneath the curve, the not the flat curve, but the curvy curve, divided by b minus a. So that's how you define the average value for a function in an interval. You just integrate the function from a to b and divide by b minus a. So, in terms of physics, a lot of times we talk about some force being applied to a body, and we say it's constant. Well, another way to think about it is it's not really constant, but if we were able to calculate the average value by into finding the area underneath the curve and then dividing by b minus a, that is the average value that we could use in our calculations, which would give us the same result as if we did the calculus part. So calculus, we'd figure the area by doing this. When we're not using calculus, we'd have to figure some average value and just multiply it by either the integral of f dx. We'd take f times x. This would be the x movement, and if it was time, that would be time. Which reminds me, has anybody seen Hidden Figures, the movie? Yeah. So I mean, I don't know if it's because I'm just a softie, or because I'm an engineer. But I cry through everything. At the end, I got tears. You think something about rockets and people who, it's funny. Yeah. Nobody else wants to admit it, but I did get a little teary-eyed there when they, their success, these women overcome adversity, and it was actually in engineering and science. It was pretty cool. So it was a good movie. It was kind of interesting, though. There were some things that I'm like, ooh, I know about that, because my PhD work was with compressible flow, which is what one of the engineering person, the one who became an engineer, she did. I read her I didn't read her papers, but I read the titles of the papers. And I'm like, yeah, I know what that is. So that was pretty interesting. When we get to chapter 6, they're talking about, if you remember the movie, and this relates to physics, is the orbit of the Mercury capsule was elliptical. Okay, we talked about that in physics, that Kepler's law says that objects that orbit around another object follow elliptical paths if they're in orbit. But then they had to convert that into a parabolic. So they talked about elliptical stuff and parabolic. Parabolic is what the trajectory of an object takes when it's not in orbit. Okay, so if we throw something, it follows a parabolic path. And so they were trying to figure out how to find the solution from an elliptical orbit to a parabolic trajectory. And they were doing it all analytically. So it was all like what we're doing in class here. And so the person, the heroine, there's a heroine thing in a STEM movie, but she goes, Euler's method, and like, what is Euler's method, right? So we're going to learn about Euler's method in chapter 6. We're going to use Euler's method. What Euler's method is a numerical technique to solve differential equations. So to transition from the elliptical orbit to the parabolic trajectory, they used a numerical approximation to get the answer. So that was kind of cool, because unless you're an engineer who's you'd say Euler's method, what does that mean? So now you'll know. You'll be able to watch the movie and go, I remember Dr. Nicholson saying, "Hey, Euler's method," and then you'll get all teary-eyed and everything, because you'll understand the significance now. And the other cool thing was the IBM thing was, because that looks so familiar. When Martha and I were talking about this when we were in college, she had to do some computer programming. Well, actually, she had to do it when she got a master's degree, which was still 1980. And she remembers punching out the cards with the data on it and taking it to the window at Tech. It was in Burris Hall. The mainframe was in Burris Hall. You hand them the cards, and you could see the reader in the back, and it would be going. Just that sound. It's like a smell memory. That was a sound memory. It was a memory of computer cards going into the computer. And so it reads the cards in. And the other funny thing was she went to the library, if you remember the movie, with her son, and she stole a book out of the library, and it was Fortran. And so that was 1961, and I did my PhD dissertation was written in Fortran still. So that was kind of cool, because I said she had the book, and I said to Martha, I bet that's a book on Fortran. And then they said, oh, it's Fortran. So that was pretty interesting. So there's a lot of little insights that was pretty good. It's a good movie, even if you don't know what the little subtle things, but okay, so the average value is this. So let's just do an example. Let's calculate the average value for this function between 1 and 3. So all you have to do is you just have to find, we'll say, f average, and really we have to somehow we'll say 1 to 3, okay, is going to be equal to the integral. I got to leave a little room here. It's going to be equal to 1 over 3 minus 1 times the integral from 1 to 3 of 4 times x squared plus 1 over x squared dx. So this is the limits of integration, but it's also what we divide by. Now I'm going to make the problem easier. Instead of using the quotient rule, I'm going to use my experience in solving these problems. Is I'm going to create two terms. So 4x squared divided by x squared is going to be 4, and the second term is just going to be 4 over x squared. And that's going to be a lot easier to solve. So we got 1/2 the integral from 1 to 3 of 4. I have to rewrite this as x to the minus 2 power. Yeah, I'm a much bigger softie than Martha is. I'm always crying about things as far as movies are concerned. She couldn't get all excited about Euler's method. Okay, so we take the antiderivative. The antiderivative of 4 is 4x. The antiderivative of this is going to be 4 times x to the minus, add 1 to the exponent, I almost did it wrong, x to the minus 1 divided by negative 1. And we're going to evaluate it between 1 and 3. So let's just clean that up a little bit before, well, what we can do is multiply the 1/2 times 4. So that's going to be 2x minus 4 over x. So what I've done there is the negative sign comes out front, move that to the denominator, and then I evaluate that between 1 and 3. So now I take the antiderivative and evaluate it at the upper limit and subtract the antiderivative evaluated at the lower limit. So that's going to be 6 minus 4/3 minus 2 plus 1/3. So this negative times a negative is a positive. This is negative. So that's going to be 4 minus 3/3. So 4/3 plus negative 4/3 plus 1/3 is negative 3/3, which is just 1. So you get 4 minus 1, which is 3. So that's the answer. So that's your average value for the function. So if we plot this function, we should be able to show that this, if we drew a horizontal line at y equals 3, we should see that the area under the rectangle defined by y equals 3 and the interval should be pretty close to being the same as the area under the curvy part. So here we go. So actually, I'm just going to delete that for right now. So delete that. Oh, that's not going to let me do that. Okay, we're going to actually plot it. And the function was, I already forgot. It was 4 times x squared plus 1 over x squared. Okay. So it was 4x squared plus 4 divided by x squared. And we're going to look between 1 and 3 and see what we get. Okay, we're going to have to zoom out a little bit. Okay, so that is the function. And what do we come up with the average value? 3. That something looks wrong. I must have done something wrong. What did I do wrong? Oh, I forgot to do the 4 part. Didn't I? No, I didn't. What did I do now? Oh, I put it in the, yeah, you're right. Sorry. Yep. So that was a good reason for checking the answer. Okay, so let's try. So, yeah, it's 4/3. And this is, that's the wrong part right there, right? So it's going to be 4/1. Right, there we go. Okay, so let's fix that. So that's going to be -4, or +4. Actually, it makes it even worse. What am I doing wrong here? Oh, I also forgot to, that should be 2, because I divided by 1/2, so let's fix that. Okay, multiple mistakes there. So let's fix all this. Okay. Does that look better? Am I doing better now? Okay, so we'd have, so I've got to fix this part too. So it's 2/x, and here we have 2 times that minus 2/1. So that's equal to 6 minus 2/3 minus 2 plus 2. So that's going to be, those will cancel out, right? So you get 5 1/3, which is going to be equal to, I'll just put 5 1/3 in there. Okay, so that's the average value. That looks a little more reasonable. So let's just grab this function, this picture here, and put it on one page. And if I draw a horizontal line at 5 1/3, which is, this is 5, so this is 5.5, so 5 1/3 is about right there. And so what we're seeing here is that, you know, this area is going to be the same as this area. And that's acceptable because this thing is slowly going this way. This one's moving up more rapidly. So the area underneath the red curve is the same as the area under the rectangle, where I take the average value, which is 5 1/3. So you take, that's the y value times the x value change, which is 1 to 3. So the area under this rectangle is the same as the area under the red curve. That's the definition for the average value. Okay, so we finally got it right. Okay, so there's your homework assignment for section 4. So again, that's a good example of where checking your answers, if there's some way to check your answer just approximately, it's not a bad thing to do. And we have 2 ways of checking our answers. One is to draw the curve and then see where the horizontal line would need to be, such that the area above the horizontal line is about the same as the area underneath the horizontal line. That would give you an idea of the average. You could also cheat and use the computer, one of those computer algebra programs, just to check your answer, which is what I do when I make up problems for the test. I always do it analytically, and then I check it online, because I don't want you to get something that's not reasonable. So that's due next Monday. I think we might have enough material to have another test before Thanksgiving. So we'll probably have a test end of next week, maybe Thursday instead of Friday, just because then I can use your study session to give you a little more time. So it would be on chapter 4, because we've only got two sections left in chapter 4. Even though the next section is going to take the most amount of time. So let's see here. Section 4. That's section 6. What am I doing? Section 5. Section 5. Where are we here? There we go. So the next section is integration by substitution, and we're going to use this so much in the future. So we're going to spend probably at least the rest of the week on this section. And it's allowing us to do more complicated integrals than we think we can do based on the limited number of formulas that we have on our integration sheet. We have some, and some of those are ones we haven't figured out yet, like the integral of 1 over x, or the integral of the arc sine, or some stuff like that. And really, integration by substitution is the chain rule in the opposite direction. We don't really have well, we do. It's called the integration by parts. That's in chapter 8. The opposite of the product rule, in terms of going the opposite. If you had a product, how do you take the results of the product, the derivative of the product, and go the opposite direction? But this is the chain rule. So what we're going to do is we're going to have a change in variables, kind of like we did when we did the chain rule, the other direction, when we use the chain rule for derivatives. So first thing we're going to do is just to look at some integrals and try to identify how we define the change in variables. Which part do we choose as, or we're going to call it u, kind of like we did with the chain rule. We had f of u and u of x. So in the case of this u substitution, or integration by substitution, we're going to have to identify some part as being u, and we're going to have to identify some part as being du. I don't really use the general power law for integration because it's just a special case of this whole u substitution. Okay, so those are the things we're going to kind of cover here. So let's just look at this integral, and we'll say, could we do this integral? And you're saying, yeah, well, I could do 2x by itself. I could do x squared plus 4 by itself. I could do something cubed. I could do x cubed by itself. But this particular combination of variables, I don't know what to do. So the question is, can I change the variables, instead of it being an integral with respect to x, be an integral with respect to another variable that allows me to use one of the formulas that I already have available, which is fairly limited. So let's look back at derivatives here for just a second, using this as an example here. So let's say I said, f of x equals x squared plus 4 to the 4th power. How would I take the derivative of that? Well, I'd say, well, I know how to take the derivative of x to the n, but I don't know how to take the derivative of this thing to some power. So what I do is I use the chain rule. I would say f of u is going to be u to the 4th, and u of x is equal to x squared plus 4. And then I take the derivative of my f of u with respect to u, So I just use the power rule formula. So it's 4u cubed. And then I can also take the derivative of this u of x part, which is 2x. And then I say, oh, the chain rule says that f prime of x equals f prime of u times u prime of x. So I plug in these, and I get 4u cubed times 2x. And I say, oh, I need to make this in terms of x, so let me go back and see what u was. So I would get 4 times x squared plus 4 cubed times 2x, and then I do a little simplification here. 4 times 2 is 8, and I get 8x times x squared plus 4 cubed. So that's the chain rule. I pick u of x to be something, usually in parentheses. I rewrite it into two parts. This is the u part, so I can change this into something that I do know how to take the derivative of. I know u of x, how to take the derivative of that, so I can do those separately using the rules that I know for differentiation, and then I multiply them together to get the final derivative. Well, if you look at this versus that, they look pretty close, right? What's the difference? Yeah, this one's 8, that one's 2. So they're only different by a constant multiplier factor. So the way you do u substitution is to kind of do the same thing. You're going to, instead of, what you're going to do is you're going to say u, and not u of x, you're just going to call it u. U is equal to x squared plus 4. It's the term in the parentheses, just like over here, u of x was x squared plus 4. Now, when you're integrating something, you need u and you need du. So in this case, I've got 2x, and I could plug in, I'd have u cubed dx, but then I've got this stuff left over. So when you do this u substitution, you have to come up with, over here we ended up with u prime. For differentiate or integration, we actually use du, because we need a du in our integration. So when you to do this is you basically do the differential form of this equation. So remember back in section 8 of chapter 3 we talked about differentials, and we said what's the differential form of the equation. So that's what we're doing here. We're finding what is the differential form of this equation. Well, the differential form is just the derivative. So the derivative of x squared is 2x. The derivative of 4 is 0. And then we multiply by dx. So we could say this is the differential form of u. Differential form, just take the derivative normally, multiply by dx. You can also think of it over here, u prime is du dx. So if we multiply both sides by dx, we'll get du is equal to 2x dx. So you can think of it two ways. You can think of it as just rewriting u prime as du dx and then multiplying by dx, or you can think about it putting in the differential form. It's basically the same thing, but the actual mechanics of getting du from u is to just take the part of the original integral that you've identified as u and take the derivative and then multiply by dx. So what that allows us to do is that, if I just move things around a little bit, so if I have x squared plus 4 cubed and then times 2x dx, I've got two substitutions here. I've got my substitution for u and my substitution for the other parts. So this part here is going to be u cubed, because u is the argument and this is the exponent, and the second part is du. So my original integral now can be rewritten as u cubed du. This one I didn't have a formula for, but this one I do because it's just a simple power rule. So the integral of u cubed du is going to be equal to u to the fourth over 4 plus c. And just like back here, when I took the derivative, when I used the chain rule, I ended up with this u thing here, but I want the answer in terms of x. So this whole transformation here, and as well as here, is just a way of transforming an integral that I don't have a formula for into an integral that I do have a formula for. Then I take the integral, and once I've taken the integral, then I can substitute u back in. To make the answer in terms of x. So instead of u to the fourth, it's going to be x squared plus 4 to the fourth over 4 plus c. So that's the answer. So I started off in terms of x, I ended up in terms of x, but in the intermediate steps, I rewrote it in terms of this variable u. Now the thing is that, if I tried to take the integral of x squared plus 4 cubed without the 2x there, I couldn't do it. Well, I can't do it right now. Okay. If I had 2x squared times x squared plus 4x cubed, I couldn't do that integral either. So it's very specific combinations of terms that allow you to make this substitution that results in something that we can integrate. And everything that we're going to integrate between now and May ultimately has to fit one of these formulas. Because that's all we know. That's all we're going to know is this. We're only going to know 18 integrations. And anything that doesn't fit that, we've got to make fit that. So let's just think about this one. What do you think I might choose as u? Remember over here, I chose the argument of the thing raised to the power. So what's the argument of this function? It's going to be x to the fourth. So that's going to be u. So then I have to figure out what du is. So du is just the derivative of this using the normal derivative rules, 4x cubed, and then add dx on the end of it. Now, if you look back at this original equation, I don't have 4x cubed dx. So there's two ways to do this, and the way I'm going to show you is I want to solve this equation so that what's not involving the main term, this one, is that I can make the direct substitution. So to do that, I just divide both sides by 4. So I'd get du divided by 4 is equal to x cubed dx. So those are my two substitutions. For x cubed dx, I can put in du over 4. And for u, my other substitution is this one. So I'm going to use those two. Even though this is my original differential form of the original choice for u. So when you do that, you'll end up with the sine of u. So this is the sine of u times du, x over 4. Okay, so x cubed dx is du divided by 4. And then you can factor out the constant, so you'll get 1/4 the integral of the sine of u du. And now if you look at your sheet, you'll notice all of them are in terms of u. Okay, you might have wondered why that was. Probably not, but you might have wondered why all those involve du, right? Why did the formulas not involve dx? Because that's what we've been dealing with up to this point. Well, that's the reason, is because if you just have x, then x equals u. But if you have something a little more complicated, in this case, u is x to the fourth, it fits into this sheet much better. So we say, well, is there an integral in our table for the sine of u du? And you're like, hey, yeah, there it is. So because of that, we can use the formula. So the integral of the sine of u du is negative the cosine of u. And because we're dealing with indefinite integrals, we add our arbitrary constant c right now. So we get negative 1/4 cosine of u plus c, and then you go back again and you plug in what u is in terms of x. So you get negative 1/4 cosine of x to the fourth. Yeah, that's right, plus c. So that's u substitution in a nutshell. But we'll do a lot more examples, because if you don't understand how to do this, you're in big trouble. So make sure you understand it. Okay, so we'll see you over in physics.